Our last section of the unit is on energy. Talk about energy, we talk about specific types of energy and how energy changes and how energy doesn't change and so on. But before we do that, we have to talk about what energy is. Does anybody remember from grade 10 what the definition of energy is? Like, it's kind of one of those things we kind of know what it is, but it's hard to describe, right? Does anybody have a definition for it? No? All right, well, I'll give you a definition then. Energy is the ability to do work. Now, energy could be actually doing work at a specific time, or it may not be doing work at a specific time. It may be kind of holding back, just waiting to do work. If it's doing work at a specific moment in time, then we would say that it's in the form of kinetic energy. And if it's kinetic energy, it's energy of motion. It's doing something. It's accomplishing something. If it's not doing work, but it's just kind of holding back, storing the energy, storing its ability to do work down the road, then we would say that it has potential energy, stored energy, energy that's not being used, energy that has the ability to do work, but isn't doing work yet. Now, there's lots of things that have kinetic energy, energy of motion. From me walking around the classroom, that's kinetic energy, energy of motion, to a car that's driving on the highway, to an airplane that's flying in the air, to an atom that's moving through some gas, to an electron that's orbiting around the nucleus of an atom. Anything that's moving is doing work and has kinetic energy. Potential energy can be in several different forms. Try to think of one situation where the energy, something has the ability to do work, but isn't actually doing it. So the electron isn't actually moving, or the object isn't actually moving. Give me a situation where it has the ability to move, but isn't actually moving right now. Danny? Perfect example, yes. When you're at the top of a hill, or even just at any height, maybe this board marker that I'm holding in my hand right now, it's not a hill per se, but it's at a height, right? What kind of energy does something have when it's at a height? Potential, but specifically we call it gravitational potential energy. The energy is stored in that object because of gravity. Gravity gives it the ability to do work, but it's not actually doing work until you let it go and it becomes kinetic. It's another type of energy. Sorry, another type of potential energy, another type of energy that's stored. Has the ability to do work, but isn't actually doing work yet. Yeah? Good. Elastic is a good example of potential energy, stored energy. Elastic potential energy, the energy stored due to the elasticity of something. Sometimes we call that spring potential energy. Take a spring and stretch it. It works the same way as an elastic, right? Stretch the spring, let it go, starts moving, right? There's other kinds as well, although these are the kinds that we deal with for the most part in Physics 20. There is chemical potential energy. How does your car move? Well, because of the potential energy stored in the gasoline in the gas tank, right? That's chemical potential energy. Electric potential energy as well, that's stored in the battery of your car. Chemical, electrical. You could even go with something like nuclear energy. Energy that's stored in the nucleus of an atom. It's not doing something right now, but it has the ability to do a whole lot, right? Nuclear potential energy. These are the kinds we're going to focus on in Physics 20. And specifically in this unit, we're going to focus on gravitational potential energy. And 2 units from now, we'll come back to elastic and spring potential energy. Now, how do we describe mathematically these energies? Kinetic energy, the energy of motion, you're going to remember this equation when you see it. We're going to say EK, the energy that's doing work right now, right? Kinetic energy, energy of motion, energy of currently doing work is equal to 1/2 mv squared. What's m stand for? M stands for velocity?
Oh,
M stands for, Josh, what is it? M stands for? Good. And the units for mass are going to be kilograms. V stands for? Go ahead, Josh. Yeah, you're close. Not quite, but you're really close. Speed. In other words, the direction doesn't matter. We're just going to sub in the magnitude of the velocity. Hey, think about that. You know, you stretch an elastic and let it go, or whatever. Like in the end, the object is moving at 10 meters per second. It's going to do just as much damage if it's moving left at 10 meters per second or right at 10 meters per second. The direction doesn't matter. The amount of work that it can do is not based on which way it's going. It's based on how fast it's going and what its mass is. EK is kinetic energy. And kinetic energy is going to be measured in what units? Did you know this? Joules. Okay, you would have learned this in Science 10. Everybody would have learned this in Science 10. Kinetic energy is measured in joules. Mass is a scalar, speed is a scalar, and kinetic energy is a scalar. Potential energy, we say we have two types or several types of potential energy. We deal with two types specifically in Physics 20, but for now, we only deal with one type actually, and that's gravitational potential energy. The equation for that is EP is equal to m times g times h. M stands for, that's mass in kilograms. G is, it's the acceleration due to gravity, so it's going to be 9.81 meters per second squared. I'll put a little star by that, because if you happen to be somewhere else on another planet or somewhere high up on a mountain, gravity can be slightly different, right? It's not necessarily 9.81, but for almost every situation it would be 9.81. Yep. That's a good question. Is it negative? No, potential energy is a scalar measured in joules. Because it's a scalar, we want to get just a positive value for it. And since we want to get just a positive value for it, then the numbers we sub in are all going to be positive as well. So m will be positive, g will be positive, and h will be positive as well. What does h stand for? Yeah, h is the height. And that's going to be measured in meters. Now, you're going to see this in a couple minutes when we go to do some problems. But the height, that can be a little bit confusing because it can be measured relative to whatever you want. Like, if I take my board marker right now and I say it's in my hand at a height of 1.5 meters above the ground, what's the potential energy of this board marker relative to the ground? M times G times 1.5, the height, right? It has that much potential to do work relative to the ground, that much potential to fall to the ground. But if I say what's the potential energy relative to my hand, how much potential does it have to do work relative to my hand? None. None. So we would say in that case the height of it is 0. Potential energy relative to the ground is mgh, h being 1.5. Relative to my hand, it's 0, because it can't do work relative to my hand when it's already in my hand. Usually we define the height relative to the ground, but you're allowed to define it relative to whatever's most convenient for you. Okay, we're going to do a kinetic energy question here on the board. This is from chapter 6 in your textbook now, if you're downloading the chapters. And it says, on a highway, a car of mass 1,200 kilograms traveling at 20 meters per second has this kinetic energy. It's equal to, it has the kinetic energy equal to a loaded van of mass 4,800 kilograms. What's the speed of the van? Tough one to start off with. Tough kinetic energy question to start off with. This car has a kinetic energy equal to the kinetic energy of a van. How fast is the van moving? They're telling me exactly what to do here. They're telling me in this question that the kinetic energy of the car is equal to the kinetic energy of the van. Agree? Look, it has a kinetic energy equal to that of a van. Hey, what's the kinetic energy of a car equal to? 1/2 mv squared. What's the kinetic energy of a van equal to? 1/2 mv squared. Notice the subscripts, though. On the left side, it's the car, and the right side, it's the van. Hey, anybody spot this? The half can cancel out there, actually, because it appears in both terms. Can I cancel out the mass? Why not? Because it's different mass. If it was the same mass, I could cancel it, but can't here. The mass of the car is 1,200 kilograms. The speed of the car is 20 meters per second. Don't forget to square that. The mass of the van is 4,800 kilograms. We're going to solve for the speed of the van. Let's find this now. Let's say 1,200 times 20 squared. That's my left side. Let's divide that by 4,800. So I've got, on the left side, 100 equals speed of the van squared. What is the speed of the van equal to? 10. So we quadrupled the mass, but the speed only got cut in half. Anybody know why the speed isn't affected as much as the mass yet? Because it's squared, exactly, because the speed is squared. Make sense? Hey, here's the good news. Most questions you get involving kinetic energy are easier than this one. Most of them are, here's the mass, here's the speed, calculate the kinetic energy. What do you think you might have to do in a just a standard, straightforward question? Here's the mass, here's the speed, solve for the kinetic energy. What's one little twist that we could throw into there? No? Yeah? Yeah, maybe you have to rearrange it. Give the energy, you have to rearrange it, solve for something else. Yeah, good. What's another thing, Patrick? Yeah, different units. If you're given grams, you got to convert it to kilograms, divide by 1,000. If you're given kilometers per hour, it's been a while since we've done this one. You remember how to convert that to meters per second? Times it by 1,000 and then divide by 3,600. Other than that, okay, this is as hard a question as you're going to see probably. Yep.
Would you ever make us convert joules or something other than joules to joules?
No, not in Physics 20. Physics 30, yes, but not in Physics 20. All right, have a look at these three questions, please, on page 303.